You know what I will try is, I will try mixed slides and the board, because I think maybe that will be little better for me. Okay. So this is the gauge group of the standard model. Everyone knows this. The neutrinos are weakly interacting. So we are not concerned about this part now. And we will be concerned about this part. Now, so you know, when you are we are writing a Lagrangian, like when I was talking about the Dirac Lagrangian, I talked about the Lorentz invariance, right? Now, when we are writing a Lagrangian which is invariant under this gauge group, the standard model gauge group, then we have to worry about the invariance under SU2L and U1Y for this part, okay? So what I will do, mostly I will need some background of SU2. So I thought that I will just do a very lightning summary of SU2, and then maybe I can go to my slides. So SU2, I think all of you know that this is a group of 2 cross 2 unitary matrices. And S means special, so S means determinant 1. So the number of parameters are, for SUN is n square minus 1, so 2 square minus 1, 3. And if we consider the Lie algebra of SU2, then this is equal to the number of generators. Okay. And we know that they obey this kind of so these are the generators of the Lie algebra of SU2 which obey the relation, and these are the angular momentum commutation relation. So we have to be a little careful about the matrices. So SU2 is a group of 2 cross 2 matrices, but the SU2 generators are traceless Hermitian matrices. In physics, they are Hermitian matrices. So the thing is that, you know, when we talk about particles, fundamental particles, what are they? The fundamental particles are actually the irreducible representations of the groups SU2. So when we are saying a doublet, that means it is transforming under the two-dimensional or the fundamental representation of SU2. So we write it like this, that supposing we write, and for this, my SU2 generators are Ji is half sigma I, where sigma I are my Pauli matrices. So supposing I call psi, which is psi1, psi2, then this is a doublet which belongs to the fundamental representation of SU2. And what is a fundamental representation? Fundamental representation is the lowest dimensional representation. Also, you should remember that they transform as this, where U is alpha is some parameter sigma by 2. So is so for the fundamental representation, the representation matrices are the SU2 generators themselves. So this is something which defines my fundamental representation. So when we take a representation, we can go, I will show you, you can take higher dimensional, like, you know, it's not necessarily 2 cross 2. But in the fundamental representation, the generators themselves are the transformation matrices. And one more thing to remember, so this is first thing. Second thing to remember is that SU2 is a real representation. So by real representation, what do I mean? I mean that I can find the S such that this is minus TS star. And this S is usually called C in this language, and this is I sigma 2. And what we can show is that if we construct C psi star, which is equal to psi 2 star minus psi 1 star. So you can calculate C is I sigma 2. This transforms, so this is equal to, we can call I sigma 2 psi star. So this transforms also as U. So what we can say is that if I consider C psi prime star, that will also transform as U. So transform as means my psi transformed as U, and then C psi prime star, that also transforms as U. So that is the similar transformation property that we have, that the I sigma to psi star and psi transforms in the same way. These are called the 2 and 2 bar representations of SU2. Because SU2 has a real representation, then 2 and 2 bar transform in the same way. And when we use mass generation in the standard model and we give mass to the lower and upper component, we need two different types of representations, then we use these. So here that is useful, okay? The other thing that we will need for our lectures is called the adjoint representation. So the adjoint representation is actually the representation where the structure constants are the representation matrices. So these represent the representation matrices, and the dimension is same as the number of generators. So for SUN, the dimension is n square minus 1. So for SU2, it is the 3-dimensional representation, which is the adjoint representation, okay? And these are the triplets, right? So we have the doublets, which are transforming as U. We have the triplets, which transform in the adjoint representation. And we have the singlets, which does not transform, which stay constant. We have to see how to write singlets if we want to write an SU2 invariant Lagrangian. Now, there are, maybe I will use that side. There are 3 ways we can do the triplet representation. One is, we write psi as psi plus, psi 0, psi minus. So this 1 0 minus means, like, for this, if I have j equal to, if I go to my angular momentum thing, then my j equal to 1, then m is 1 0 minus 1, right? So this is, in this, my psi prime will transform as exponential minus I alpha I ji by 2 psi, where ji will be my angular momentum matrices for j equal to 1. So these are 3 cross 3 matrices in the angular momentum, which we already know for j equal to 1 representation of the angular momentum. Another way of writing it is as psi1, psi2, psi3, where my psi prime transforms as alpha I tau I by 2 psi, where my tau I is I epsilon I j k. So these are the structure constant matrices, okay? And you know, these two are related. We can do a similarity transformation and we can relate this. So that's always when we are teaching group theory, this is a good homework problem which we always give, that you know, you find the basis transformation which relates these two. And that will give you this, like supposing you have these states pi 1, pi 2, pi 3 and pi plus, pi 0, pi minus, and how they are related. So these are the two options. There is a third option which is used most excessively, and I will tell you why that is most popular, and I am sure you have seen it before. Another is I write psi as half sigma I psi I. This is equal to psi 0 by root 2 psi plus psi minus minus psi 0 by root 2, where psi plus minus are psi 1 minus plus I psi 2 by 2. So this is, we can also represent a triplet or adjoint representation by a 2 cross 2 matrix. You must have done it, for instance, you know, for the W bosons you have seen that this 2 cross 2 matrix is used. So, and the advantage of using this is that, you know, this psi transforms as U psi U dagger, where U is my 2 cross 2 matrix in the fundamental representation. So that's why here, you know, instead of using the 3 cross 3 matrices, in this we can use the 2 cross 2 matrices, but it is transforming as U dagger. These things actually, you know, you can show. I have no time to show, but I just wanted to tell you the different kind of SU2 representations that are that we are going to use. Okay. So now what I want to write are the SU2 invariants. These also I will write. Maybe I will show a easy one. So number one is psi dagger psi. So this, if we consider psi dagger prime psi prime, then I can write it as psi dagger U dagger U psi. So then this is psi dagger psi. So like for the Lorentz group, I told that psi bar psi is an invariant. If we consider only SU2, psi dagger psi is one of the invariants. Okay. Now, this is another one which I am not showing because one has to do some index algebra, which is this C I sigma 2. I can write it as a second rank tensor epsilon AB. And you can show that this is an invariant under SU2. And the third thing that you can show, see, the thing is that I did it in a simple way. Usually what you have to do is you have to write in the notation the covariant and the contravariant. One is transforming as U, another as U star. And then you can show with the index. So another thing which is a singlet, which is psi transpose epsilon psi. So if you have not checked it, or if you have checked it, you can check, or you can, remind yourself if you have forgotten. So what we do, like when we are writing a Lagrangian in the, for the say the standard model, I have the doublet fields. I am making it, it is interacting with some other field when I am writing. Then I have to have some combination, right? So So supposing I have a 2 doublet, 2 cross 2 or 2 cross 2 bar. This you know, right? What is this for SU2? 3 plus 1. So what does this mean? Can anyone tell me in terms of group theory? Yes? So, yeah. Triplet, yeah. Triplet and singlet, that is true. So I am combining 2 doublets to get a 3-dimensional representation and a 1-dimensional representation singlet. So these are the irreducible representations. And this is what you do in the Klebsch-Gordon, right? That you combine, and in the group theory, I say I combine irreducible representations, which I did for the Lorentz group also. So this is very important, and I find it really amazing that, group theory and particle physics did not develop like together, but when you consider these group representations and the fundamental particles fit in so nicely, so that's really, I like this group theoretical approach to understand these things. So this is one thing. So I know I have the doublets in the standard model. I know how I combine 2 doublets to write a singlet. I know. How do I write a triplet? In the standard model, does anyone know that when you write a triplet term in the standard model from 2 doublets, what will you write? So we write this as psi dagger sigma I psi, where sigma I are the Pauli matrices. And what we can show is that if psi goes to 1 minus alpha dot sigma by 2 psi, then you can see that this transforms as a vector under SU2. So this I call V prime will go to V minus V cross alpha. So this is like our vector transform. So this is like a triplet. So these are the things we should know, that when we are writing a Lagrangian, then the basic SU2 is this, that we have at least for the standard model and the part that I am doing now, we are doing the fundamental representation, which is a doublet under SU2. Then we are doing we will use the adjoint representation, which is the triplet under SU2. Okay, so I will go back to slides now. If you have any doubt, you let me know. I think it's okay with the slides now. So, because I have explained what is needed to understand the slides. So you already know that there are 3 neutrinos, and they are coming in 3 flavors. These are left-handed. So these are doublets under SU2. Of course, I have not mentioned this U1Y, which is the hypercharge, and it is related as Q is T3 plus Y by 2. Okay. So now if I write here, so supposing I write here nu E. Now the SU2 here that we are considering is the isospin, right? T3. And Y is my U1 quantum number. So this has T3 plus half and this has T3 minus half. And I know Q is T3 plus Y by 2. Now for the neutrino, Q is 0 and T3 is half plus Y by 2. So that gives me Y as minus 1, right? Similarly, the right-handed leptons occurs as singlet. And if here it is singlet, so the SU2 quantum number is 1, means this is a singlet under SU2. So here I find that, say the charge is minus 1, then minus 1 is Y by 2, so Y is minus 2, right? So these are the hypercharge assignments. We have the antiparticles also, as we have seen. So the particles are in the standard model, we have left-handed neutrinos and right-handed antineutrinos. We don't have any right-handed neutrino, like we have the right-handed charged lepton. In the standard model, we don't have the right-handed neutrinos, and that was incorporated to to have, because have parity violation. So that was perfectly fine. Now let us see about the lepton number. So neutrinos are electrically neutral, but they carry lepton number +1, and antineutrinos carry lepton number -1. And what is lepton number? Lepton number is a global U1 symmetry, so that if psi prime goes to e to the I alpha psi, that is the lepton number. It was introduced in 1953 by these people to explain certain missing decay modes. So for instance, we have this kind of decays you have seen in Andres and other lectures, that pi to mu minus nu mu. And these kind of decays are rare, like it has not yet been seen. So this says that Le and L mu are not conserved. If this happens, then Le and L mu not conserved separately. But here we are seeing that known decays, that lepton number Le, L mu and L tau are conserved separately, as well as the total lepton number. Okay, so that is the thing about the lepton number. Now the question is, how do we generate the fermion mass in the standard model, and why neutrinos are massless? So in the standard model, we have a Higgs doublet, which is phi plus and phi 0. Again, I have this 2 and 1, because my Q is equal to, so this is the doublet, this is half, T3 is half minus half. So from there you can get that this Y is +1, right? Now the procedure of mass generation in the standard model is through the Yukawa coupling and the spontaneous symmetry breaking mechanism. So we can write a term like this in the Lagrangian, psi L bar phi ER. So I have here a phi plus and phi 0. Again I have T3 half minus half, and if I take this one, then Q is 0. So T3 plus phi by 2, so my Y is +1. And for the leptons, I know Y is -1. And then what I can write here? I can write a term, Yukawa Lagrangian will be YE, some coupling. I write psi L bar phi ER, say. Now, whenever we write a term, we have to see that all the quantum numbers are satisfied. So first of all, I have two doublets here. If I didn't have the Higgs, then I could not have written this psi L bar ER term, first of all from SU2, because I had a SU2 doublet and a singlet. So that term is not allowed. So first I have a phi, so my 2 cross 2 is 3 plus 1. Now the Y was -1 for the lepton doublet. So now the psi L bar is side L dagger, so Y is +1, phi Y is 1, and ER Y was -2. So the Y is also satisfied. So we have to see that everything is satisfied, and here you can see Y is dimensionless. This is called the Yukawa coupling. Now when the Higgs develops a vacuum expectation value, then if you calculate this term, then what will you get? I will get here nu L bar EL bar 0 V by √2 ER. And if I calculate this, then I will get EL bar V by √2 ER. So this is giving the mass to the electron, right? So the electron mass is in terms of the vacuum expectation value of the Higgs, the Yukawa coupling. Now this is not a prediction of the standard model, because this is arbitrary. And then when we include other leptons and quarks, there are different Yukawa couplings. So these are all free parameters. So this is the usual direct type of mass. We don't have this type of mass in the standard model, because there are no right-handed neutrinos, because for this we need the right-handed state. So one of the simplest possibility to give mass to the neutrinos, a direct type of mass, is I just add a singlet right-handed neutrino to the standard model. Then I can write a mass term defining a nu as nu L plus nu R. So here I say that nu L and Nr have the same lepton number. So nu bar nu conserves lepton number. And then the mass will be generated by Higgs mechanism usually. So this is the I wrote. If I write the Hermitian conjugate term, I can write this in the same way. LL bar or psi L bar, whatever I call it. Then phi V, sorry, phi tilde and NR. Now you have to see that I am using phi tilde, which is I sigma to phi star. Because if I don't use I sigma to phi star, then I will not be able to give mass to the upper component. Because the phi which is giving mass to the lower component will not give mass, because here if you do, then you see that nu L is not getting the mass. So for giving mass to the nu, I need the upper component. And for that, I have to use this I sigma to phi star, which will put this V up. So that is the importance of the two-bar representation that I talked about, that same phi cannot give mass. So now this is one way. Let me talk about the Majorana mass, that in the standard model, can we have a Majorana mass? So let us see the quantum numbers. So the nu L has 2 minus 1 and nu LC will have 2, 1. So if I write a nu LC bar nu L term, then I can get a singlet of SU2 or a triplet of SU2. But when I combine the Y, then the Y is always minus 2. So the Y is not conserved. So then I cannot write a Majorana term in the SM. What I can do is, with this I can add another term which has to ensure that Y is conserved as well as the SU2 is conserved. Now one option is to add a scalar triplet. So here I have a 3 minus 2. I can add a 3, 2 with it. So another scalar triplet with Y equal to 2. So that I get this 1, 0, which is my singlet. So this is one way of, we can also use this 1 minus 2 and try to see if we can give a Majorana mass term. So this is one way of adding, so I can add a triplet scalar. But then one has to worry about other things, that whether the right-handed neutrino is a singlet, so that's not a problem. But if you add a scalar triplet, then you have to worry about whether, the agreement of the standard model with the data is spoiled or not. So all those things one has to worry about. But these are the, in principle, possibilities. Okay. So what happened to the lepton number in the Majorana term? Let us see that. Because this we had nu LC bar, you know that nu LC bar is nu LC dagger gamma 0, and nu LC is nothing but C nu L bar transpose, then I have dagger gamma 0, then this is nu L transpose gamma 0 transpose C dagger gamma 0. So then this nu L, we can write gamma 0 transpose C dagger gamma 0 as C dagger. This is from the previous day. If you see your notes, you will see. So ultimately, I am getting this as nu L transpose C dagger. So nu LC bar also I can write as nu L transpose C dagger. And then if you see that, if I have a global gauge transformation where nu L goes at e to the phi nu L, transpose will also go like that. So I will have this lepton number sitting here. So this is not invariant under the global U1 gauge transformation. And if I say that, this phi eigenvalue is 1, phi value is 1, then the lepton number is violated by 2 units. And you have seen today morning, and you will see more lectures on neutrino-less double beta decay, which will occur if there is a lepton number violation. Now, so like supposing if you consider charge, then charge also will be violated. That's why charged particle cannot be Majorana. However, the electric charge is like, it will spoil the gauge invariance if we break the electric charge. But the lepton number is kind of an accidental symmetry in the standard model. So the lepton number can be violated. And that's why the Majorana neutrino is a possibility. So now what we have to see is that what is a Dirac Majorana mass. So supposing I add both kind of terms in the standard model. I have a nu L C, I add an NR, then I will have nu L C bar ml nu L, this we have seen. Then I can have a Majorana mass for the NR also, NR C bar NR on Hermitian conjugate. I can also have a Dirac term MD nu R NR bar nu L. Now yesterday someone asked me about the half. Now you see, when I am writing a Dirac term and the Majorana term, I have to be careful that there is a factor of half taken because the degrees of freedom are half here, actually, independent degrees of freedom. Now what we do is, we break this NR bar MD term into two terms. And I want you to check this. I will wait for 2 minutes and I want you to check that I can write this NR bar MD nu L as this. So I will take little rest and you can check that. And if you have any doubt, you let me know. You can do it from what I have done yesterday. You have to look into that property. I found it easier to do it this way, but if someone can done this way also, that's good, no problem. I believe I did it this morning, but where is it? Here. So, when you do this, there is a trick involved, which is that if we consider a scalar and we take a transpose, then it remains the same. This is one thing you have to remember. Another thing you have to remember is when we consider these fields, these are fermion fields, so they are Grassmann variables. So if we exchange them, there is a minus sign. So anyway, let me do one so that you can do the others. So whenever we are dealing with these Majorana fermions, then we have to do all these things many times. So I am writing this as nu LC bar MD transpose NRC. And I am writing this equal to its transpose because it's a scalar, I can take the transpose. So I am writing this as NRC transpose and minus signs because this order is changed. Then MD nu LC bar transpose. Then this is C NR bar transpose. So I have shown earlier that nu L C bar can also be written as nu L transpose C inverse. So then I am getting NR bar C transpose MD C inverse transpose nu L. Now C and MD are in different space. Anyway, here my MD is number. So this C transpose C inverse transpose is 1. So you get NR bar MD nu L, right? So this is equal to So, this is a question we always ask whenever we are going for a thesis viva or something, that why this MD transpose is coming. So this is a very important question. If you should always remember that how you are writing this MD transpose, because eventually you want to write this in terms of this field NL, nu L, NRC and nu LC bar NR, and overall this is like a Majorana mass term. So if I get time, we can do the diagonalization of this, like I have done the eigenvalues. You can find the eigenstates and we can see that that these are indeed Majorana neutrinos in general. There are different limits which one can take. So the point is that when I have this Dirac term, I break it into two parts, and because this part is equal to this part, I can write it like this matrix, mass matrix, which is ML, MD transpose, MD, MR. And in this basis, nu L NRC, and this NLC bar is nu LC bar NR bar. Now, if I have one generation, then MD and MD transpose are same, and then I can do this this diagonalization very easily because it's just a 2 cross 2 matrix, and I can get the eigenvalues in terms of this ML, MR like this. Now, supposing we assume ML as 0 and MR to be much greater than MD, then what we get is that M prime 2 is approximately MR and M prime 1 is approximately minus MD square by MR. So here what I am getting is that, there is a suppression by a MR, and this is called the seesaw approximation. So we will see what it does mean actually when we try to do seesaw from some, at a more fundamental level. So if you have any question, you can ask me. If there is anything not clear, then you can ask me. So it is nothing, I just wrote both Majorana and Dirac terms so far what we have written. Then I just break it into 2 terms and I have shown you 2 tricks. One is take the transpose and one it is when a Grassmann variable you change the sign. Then you get this, and this diagonalization is very easy, and this is the seesaw. So the question is this, that that the seesaw, we ask the question that is the smallness of the neutrino mass related to some new physics at high scale. So we are saying that this MR is a high scale where there is some new physics, and if I do a real matrix, if I take MD and MR as matrix, then this M comes as MD transpose MR inverse MD. Because I took as number, it came MD square by MR, and my MD is nothing but Vy nu, because if you can check here that this, okay, I will show later that. So that MD will come from the usual Dirac term. Now, here let us see some order of magnitude, that the neutrino mass is small. Why this works? Because the neutrino mass, we know from now, you had several talks, so you know that neutrino mass is of this order, say 0.05 electron volt. Then if I have MD 100 GeV and Y nu 1, then I will get this, the neutrino mass from this as 0.05 eV. If I take MR as 10 to the 16, MD 100 GeV and Y nu as order 1. Now, I showed you that when we are having the seesaw, then when I added a new R, then I had a term like, if I have a term like Y nu V by root 2. If I have this kind of a term, which I had for the, say for instance, for the electron. So for the electron, I said that, I have a mass term of this form. And what happens is, when I add a right-handed neutrino, and I say, okay, you can ask me what is the problem. You add a right-handed neutrino, you give a Dirac mass. The problem here is the following. Then when if I have my M nu as this, Y nu V by root 2, and if I want M nu, say of the order of 0.1, and if I assume my V as 100 GeV, which is, V is the vacuum expectation value, so V by root 2 is about 176 GeV. If I assume this as 100 GeV, so this is like 10 to the 11 electron volt, right? So for Y nu, M nu to be 0.1, my Y nu has to be very small, like 10 to the minus 12. So if I want to give a neutrino mass, a Dirac type of neutrino mass, just by adding a singlet, then my coupling is really small, and it's not really natural in the sense that, we have a small number in the theory if there is some symmetry, but it is not protected by any symmetry, so that's not natural. Another thing is that, it's not very interesting, because if we have a singlet, if we have a small coupling, that's it. After that, we don't know, how to probe this, because this coupling is so small. But we will see that, the seesaw can provide us so much more thing, because, the seesaw is giving us this, that's some new physics at high scale. So that is what the small, you want to ask something? Yeah. Yeah, yes. But then, the charged leptons are like the YE is around 10 to the minus 6. So this is even too small for that. There are, so that is not really considered as very natural. So then, now the thing is that how we can get the seesaw, what is the origin of seesaw? So this is in 1979, Weinberg showed that if we give up the renormalizability of the theory, then we can write a dimension 5 operator in terms of the standard model fields. Now what do I mean by that? So far whatever Lagrangian we write in the standard model, it has mass dimension 4, and the coupling is like you have the mass dimension, or if you consider lambda phi 4, then you have dimensionless. But we don't have negative mass dimension couplings in the model. Because if we have negative mass dimension coupling in the model, then when we do the renormalization, like when we try to cancel the infinities, then there is a problem. Because the negative mass dimension, just very basic way to understand is, adds a negative power of momentum in the denominator, and then it becomes difficult to cancel it by, if you do cancel it at one order, the next order again that infinity can appear. So it's a little technical thing, but the negative mass dimension is a problem. But Weinberg said that if we consider that, then we can have this kind of operators. This is the famous dimension 5 Weinberg operator. So what happens is that this, after electroweak symmetry breaking, this H gets wave, then the neutrino mass is of the order of kappa v square by m. This C5 is kappa m, and m is the scale of the new physics, and if m is high, then you can have a naturally small neutrino mass. Okay, so this is a natural way of generating neutrino mass. Now, another thing is that if you see this, I have not written it in a proper SU2 way, but this L and L I have, it comes in a way that this operator violates lepton number by 2 units. So this implies that neutrinos are Majorana particles. So because the other fermions have different mass, and if you remember, Andre showed you the mass spectrum of the fermions, that neutrinos have very small mass. So people think that this question is really natural to ask, that whether the lepton number violation or the Majorana nature of the neutrino has something to do with the smallness of the neutrino mass. And here, like the correct neutrino mass is getting like 10 to the 15, 16 GeV, which is also the scale of the grand unified theories. So all this looks really nice, that because you can get a neutrino mass in this manner in the realm of grand unified theory. In fact, if you consider SO10 models where like the right-handed neutrino comes naturally, and we can implement this kind of seesaw naturally. So this is the thing, that I have a LL phi phi operator, and when electroweak symmetry breaks, this phi gets a wave, and then I can give a neutrino mass. Now the question is that, so this is a non-renormalizable operator. So this is like an effective theory, that I write the standard model Lagrangian, then I write the non-renormalizable effective operators like the D equal to 5, this is the lowest dimensional, then I can have higher dimensional operators. And this, like, so there can be a scale below which it's effective, and there can be a scale, and above that I can write maybe a Lagrangian which is not renormalizable. So one of the example that we know is the Fermi's theory, right? When we do the weak interaction calculations using Fermi's theory, then we take this kind of a thing, right? At low energy, when Fermi proposed, it was an effective interaction. But now we know that, that we have the W plus, and what we are doing, we are actually in a momentum where the W mass is very large. So we are taking the W mass. If we have the propagator, we take the W mass out. That's why GF has a 1 by mW square in the denominator, right? So So this is the similar case with the seesaw. And now this is, we will see little more of that. But now let us see that group theory wise, how can I get this kind of term in the Lagrangian? Because my group theory, I need to have the this as a singlet term. So there are various possibilities. One is that, you know, L and phi forms a singlet. Then I have a 2 cross 2 is 3 plus 1. I can get. So this kind of term will be mediated by heavy singlet fermions. This is known as the type 1 seesaw. Another type is where the L and L forms a triplet and phi form a triplet. So then I have a 3 cross 3 of SU2, which also gives me a 1. This is mediated by heavy SU2 triplet Higgs. And another is the type 3 where my L and phi form a triplet. This is mediated by SU2 heavy triplet fermions. And what do I mean mediated by? Because it arises because of a tree-level exchange at a high scale. That high scale is similar to the heavy particle mass. Now you can ask me, if I have a L and phi forming a singlet, then can I give a neutrino mass? If you write your Lagrangian, then you see that this term will not give us a neutrino mass. So now I have told you that how we can write. So you know then how we can write, because I have already discussed how we can write a singlet in terms of two doublets, right? So here I write phi transpose epsilon LL, what we have shown. This LLC bar, we have to see all the quantum number conjugation, but C bar is also related to transpose. So this is a singlet. Then I have a L phi forming a triplet. So I have this sigma I epsilon, because I have shown you earlier that, you know, this one, sigma I, if I write with that, then that is a triplet. And then I can also write here, sorry, L and L, this should be L and phi forms a triplet. So there are three ways of writing it, and then you can ask me that why there is only one Weinberg operator. And this is some algebra of SUN you can do, and you can show that these are not very difficult algebra, but difficult to do here within 1 hour, that all these are equivalent. So the three different seesaw actually has the same basic structure for the dimension 5 operator. If you have not done this, and if you are working in neutrino mass, I will request you to do this. If so, you know, you can check it and we can discuss next week. Sometimes we can take one tutorial where we can discuss if you have any doubt. Tutorial means people have to come and do, the madam will not do. So then it's your choice whether you will come or not. So now I will show you that how do I get, like I told you the group theory and all. Let me write a Lagrangian, let me write the diagrams and just show you. You know, it's very easy when you are teaching, you can leave the difficult calculation for the students. So that's a good trick you learn when you are teaching. So what we are writing is that, you know, I have a right-handed neutrino in a type 1 seesaw. So I have a nr bar gamma mu del mu nr term is the kinetic term. Then, you know, I have already written this in, when I wrote a Dirac mass term, then how do I write y nu phi tilde? I have a Majorana mass term. So this is my Lagrangian at the high scale. And what I do is I take this Lagrangian, I have to take the Feynman rules, and here you have to be little careful because we have to use the Majorana fermion Feynman rules. So it's your usual standard calculation, but the Majorana fermion Feynman rules are little different. And if I have to do it, I at least need 2 lectures to do this, so I will give you a reference. But then what happens is that, so then you write the possible diagram. So I have this L phi, and I can have this T channel and S channel diagrams. And what I do is integrating away means, in our language, I can take P, this M, when MR is very heavy, then this MR from the propagator will come below as 1 by MR. This is like the 1 by MW for the GF, right? So this will come below, and this side is nothing but this this is singlet, this is a singlet. So this side is my L5, and you can calculate this side. and when you equate this side, you get the seesaw relation. So it's not very, once you know the Feynman rule, this calculation is a tree level calculation, so it's not very difficult, but you can do this calculation and then you can, so what I want to explain is that, you know, when we say seesaw, it's little more than MD transpose MR inverse MR. It comes from a UV complete theory where we are adding a right-handed neutrino to the standard model. That is a minimal thing that minimal field addition, the type 1 seesaw, and I can calculate this side. I know what is this side already from what I wrote, and once I do this calculation, I can equate both sides and I can get that this kappa. So this will give you from these couplings, you know, here you have y nu, you will have y nu transpose, that will transpose will come from your Majorana-Fermion-Feynman rule. This MR will come from the propagator. So this is the type 1 seesaw and the type 2 seesaw. Now, you know, I have shown you that a triplet can be written as a 2 cross 2 matrix, right? And if you write this, so if you write the corresponding like this, then this is delta plus plus, delta 0, delta minus. And then you can see that this y has 2. The hypercharge is 2. So I add a y equal to 2 scalar. I can again write the Lagrangian. Here I have only one diagram because I don't have a L phi delta coupling. I don't have. I have a phi phi delta coupling, which is not being shown here, but phi is a scalar. So this phi phi delta coupling is coming from the scalar potential. And I have a LL delta coupling here, and here this scalar has a lepton number. So that's how there is a lepton number violation and we are getting a mass term. So this is the type 2 seesaw. From here also I can get a small mass term for a this value of m delta square, like a high value of m delta. I can also have a type 3 seesaw. This is like the type 1 seesaw. This is a triplet fermion, but here I have y equal to 0. So here my fermion field is like sigma plus, sigma 0, sigma minus. So that will be y equal to 0. So here it is like, again, it's the type 1 seesaw. Only thing is that this is an SU2 triplet. Again, you can do this and you can get this type of a seesaw relation. So then the thing is that what are the implications of seesaw? One is we have already seen Majorana particles, so neutrinoless double beta decay is possible. Another very interesting implication is the procedure of leptogenesis, that, you know, because there is lepton number violation, these heavy mediators can decay to lepton Higgs and their antiparticles and can contribute to the baryon asymmetry of the universe through the process of leptogenesis. There have been lot of work on testability of seesaw at LHC, where I am saying that new physics scale is 10 to the 15 GeV, but when the collider results came, then people thought whether seesaw can be at low scale. Then people considered lot of, you know, TeV scale seesaw, and there can be lepton flavor violation also in these models. And there are some variants of the models like the inverse seesaw models, etc., where, you know, one can also get this kind of low scale seesaw. So I think that, yeah, these are the two things I read very much, which is that this is the paper by Denner. Like at least our group, we follow these Feynman rules. And this is a thesis by John Karsten, where the type 1 seesaw is worked out in very detail. So we have studied from here, and they are also using these Denner's Feynman rules. So I think that, yeah, maybe I should stop here because this part can be done later. Yeah, and if you have any questions, then maybe. So if there are no questions, there are two reasons. One is it's very clear, and one is very unclear.
No, there will be tutorial. So
I think I will take it as very clear.
Okay, let us thank her again.